Okay.
It's not winter.
I know, it's not winter. You're right. You're right.
Why is
Okay.
it snowflakes?
I don't know. Okay, so
And they're
let's.
they're not unique. There's
not.
matches.
I know they should. They should all be unique. Okay, so let's have a look here. So I want to look at a couple things. First thing is not important. It's really not, but I want you to know about it. An honors class is something you need to be aware of, but it's really not that big a deal. I'll tell you why it's not that big a deal. It's called the rational root theorem. Some people call it the rational zero theorem. And here's what it says. If you've got some polynomial, right, with a leading term, a sub n times x, and that really should probably say x to the n there. But the important thing is that the leading coefficient is a sub n. And the constant term is a sub 0. Then what we know is that if that polynomial has rational zeros or rational roots, and what does rational mean? Okay, if you write it as decimal, it's either repeats or terminates, right? Okay, but what is it? What does the word ratio really mean? Fraction. Okay, so if it has zeros that can be written as fractions, and integers really are just fractions, aren't they? With what denominator? 1, right? 2 is really just 2 over 1, isn't it? Right. So if it has, and it may not. And that's really why this is such a weak theorem, because it may not. They may not have any rational zeros, but they may still have real zeros. So this only works if they have rational zeros. But if they do, this has to be the case. Oh, there's the n, I guess. Okay. So all of the rational zeros have to be in the form p over q, where the numerator p is some factor of the constant term, and the denominator q is some factor of the leading coefficient. Okay? So what's that mean? Okay, let's look at an example or two, and then we'll just move on, because it's really not, this isn't that big a deal. So for example, what if we had something like this? Find the rational zeros of x cubed plus 2x squared minus 11x minus 12. Okay, so what's the, we remember we want our rational zeros. They all have to be fractions built from, on the numerator, the factors of, thank you, the factors of the constant, and on the denominator, the factors of the leading coefficient. Okay, so what's that mean then in this case? I don't have anything left on this one. We're going to do this one on our own. So what would the numerator be? If they have to be, oh, whoops, I don't want to do that.
I got rid of it.
There we go. Okay, so it's a good color for against the blue orange. So what would the numerator, what are all the possibilities for the numerator? Let's give it, thanks. So what are all the possibilities for the numerator? And they could be positive or negative factors. So what could they be? What are the factors of 12?
3, 4, 2.
3, 4, 2, 1, 6, 12. Okay. So plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, plus or minus 1, right? Okay, lots of possibilities. That's really a pain. But the nice thing about this is, at least the denominator, q, what are the only factors of 1? 1 and negative 1, right? And dividing by positive or negative 1, all that's going to do is just change the sign of the numerator, right? Does that make sense? So really, it doesn't change anything up here, does it? If q equals plus or minus 1, then all this stuff right here, that's really just equal. Those are all the possibilities for P over Q, aren't they? Everybody agree with that? Does that make sense what I just said? Okay. So those are the only ones we have to try. How would we try those most conveniently? How would we test to see if any of those are zeros? What do you think? Well, okay, we did that. What's positive? What's plus or minus 12 divided by plus or minus 1? Is it just plus or minus 12? Right. Plus or minus 6 divided by plus or minus 1 is plus or minus 6. But how am I going to test those? Those are obviously all those can't be zeros, right? But potentially one or more of those could be. I could, right, and that's really all. I just want to see if any of those give me back 0 for my function. But we have a really quick way of doing that. What's our method for doing that? Yeah, synthetic bracket, right? We would just do this. We would just take this function, whose coefficients are 1,
2, negative 11, negative 12.
negative 12, good. And we try all those out front. Now I'm going to try something really tricky here. I never thought of this before, but this would be, I guess, a good way of doing this. I think if I, whoops, something not normal happened there. Let's try that again. I think if I cut and paste that, I can't erase it. Let me just try this. I don't know what it's doing.
Maybe go into the selector and then try and see if it gives you different.
There. Oh, wrong thing. I wanted that, didn't I? Oh my gosh. That's what I want to do.
That's weird. It's the background.
Yeah. Okay, so there's our example. Okay, so we'll just run these things through synthetically and see if any of them work, right? That's really what we're doing here.
Oh, the graphic math.
Okay, so close. Yeah, it's close. Okay, so now we'll just try them. Like I could try 1, for example, and we'll just see if it works. If I bring the 1 down, 1 times 1 is 1 plus 2 is.
3.
You just stop me when you know it's going to work or not. 1 times 3 is 3. Not going to work, is it? Can you see it's not going to work?
Yeah.
Okay, so we'll get rid of those. Okay, so the 1 is out of there. The positive 1 is out of there. Negative 1. 1, negative 1.
No.
It's not going to work, is it? I'm getting numbers too small. Not going to work, right? Everybody agree?
Yeah.
Oh, is it not going to work? It might work. Negative 1. Negative 12. Oh, I get, yeah, it does. That does work. Okay, so I get a 0 there. So negative 1 works. And now if I wanted to find the other ones, be smart about this. How can I find the other ones really quickly? I'm trying to find the zeros. I mean, I could make another synthetic division bracket, but I don't have to. What am I left with here?
Oh, negative 12.
I'm left with, what is that polynomial? It's quadratic. That's x squared plus x minus 12. All I have to do here is just set that equal to 0 and solve how? How would I solve that one?
Fill in X. That's P.
Now come on, think about it. If you've got a quadratic equation,
X is going to be.
like what, focus. What would we do? How would I could do quadratic formula, sure. I could easily do quadratic formula, that would work. Can I find magic numbers?
No.
That multiply to negative 12 and add to 1.
3 and negative.
Yeah, there you go.
4 negative.
Positive 4, negative 3. So this is one I could solve by factoring too. But I could also just use the quadratic formula. So what are my other two zeros? Once I get one of them, I'm set, aren't I? Because now it's no longer cubic. And I'm back to chapter 5 stuff, and finding the zeros of a quadratic function is easy, right? I can always fall back on the quadratic function. It's just that when I get a polynomial bigger than quadratic, that's what chapter 6 adds that makes it harder, right? So then what are my other factors? Negative 4, positive 3. Good, so I got negative 1, positive 4, whoops. Did I get that wrong? Oh, negative 4, positive 3, right? Those are my three zeros. Once I get one of them, the other ones come pretty quickly, right? Get the idea? That's probably enough for you guys. I don't think you guys really need to even go through another example. Let's just look at how we would do this. This would be a harder one, wouldn't it?
You have to find 2 before you can.
This would be, okay, yeah, because it's quartic. That makes it hard. But also because if you look at the P and the Q, what's P in this case? Factors of 12, again, right? That's a bummer. So plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, plus or minus 1. Yikes. What about the factors of the leading coefficient?
10, 5, 2,
Plus or minus 10,
plus minus 5,
plus or minus
plus
5.
minus 2, plus minus 4.
So I got a ton of stuff to try, right? Now, if I were going to do this strategically, the easiest ones to do would be the integers, right? Those are the easiest ones to run through synthetically. So I'd try Q equals plus or minus 1 first with those. Then I'd probably start to, 2 goes into some of these evenly, so I'd probably use 2 next, right? But you can see already that this is going to be a pretty exhaustive process. Not worth messing with. It's really not. You know how to do it. Synthetic division is how you test the zeros, right? All this rational root theorem tells you is a list of possible zeros to try. That's it, okay? But once again, it's really of marginal value because it only gives you the rational ones, not the irrational ones or the imaginary ones, right? So if we ever want to find the zeros of a function for solving a real world problem, what do we do? How would we find the zeros of this if we had our graphing calculators available? What do the zeros, the real zeros, correspond to? So if I go back,
When they go over the y.
when they go over which axis?
X.
Because I'm setting, if I want to know when this equals 0, yeah, I want to know when is the y value equal to 0. That's going to be on the x-axis. So remember, this is important, and we'll pull this all together at the end of the chapter a little bit, but the real zeros correspond to x-intercepts always, right? And so if we're looking for those, the easiest way to find these things would just be to graph this function and find all the x-intercepts, right? Find the zeros graphically, okay? Make sense? So that's how I'm justifying just breezing through that section without really doing anything. It's not that important. It's not a Common Core standard. It's not. I mean, it's been dropped. And for good reason. I think it makes sense. All right. So moving on. Oh, okay. I'll just mention this. Once again, I'm not going to waste time doing this problem. But also understand this. Understand that zeros could be. They could work more than once, couldn't they? There's no reason that just because on that example we did, which is the one that worked, -1. Just because -1 worked once, does that mean it couldn't work again? No, it could. It certainly could, right? I could get -1 as a double zero. That just means if -1 is a 0, so f of -1 equals 0, what's the factor that goes with that? X plus 1, right? So that means this goes with a factor of f of x would be x minus -1. Well, what if -1 were a double zero, if it worked twice? What does that just tell you? If I factored it, how many of those factors would I get? 2. So I'd get an x plus 1 squared, right? Does that make sense? If -1 is a zero that works more than once, it just means that it is a multiple factor. Okay? And once again, we'll get into this in a different way that I think makes more sense here soon. Okay, here's what I want to get to though. This is big time. Yes, sir.
Oh, Renee, one more time, she's waiting for the draw grades or something.
Oh, okay. Okay, I'll do them
She's
middle
looking
lunch
at her
today.
screen.
I'll do them at lunch today. Tell her that. Okay, so fundamental theorem of algebra. This is big time. What the fundamental theorem of algebra just says. Now, I've already told you. Do you remember what it is? You fill in the blank. A 4th degree polynomial has what? You remember? How many zeros? 4th degree? No. No. 4. Okay, now they might be imaginary. Some of them might be imaginary, but it always has, an nth degree polynomial has exactly n zeros every time, okay? Now, some of them could be multiple zeros. Some of them could be imaginary. But if we want to find all the zeros, we know that we have to account always for whatever the degree of the polynomial is. That's how many zeros it's going to have. So, for example, this guy right here is a cubic polynomial. We know it has to have, guaranteed, it has 3 zeros. In this case, if we were to solve this one, we'd find that they're all real. Okay? And these are our 3 zeros. But they don't always have to be. They could be imaginary also. Now, the other thing we know, though, the other clue we get, because you're going to be doing essentially 2 important things in this section. You're going to be, well, I mean, you've already done finding zeros. That's something you've already had a lot of practice with that. So we'll be kind of fitting that to the fundamental theorem by saying, okay, how many zeros does this have to have, and what are they? But the other thing we'll do is we'll turn that process around and we'll say, okay, if these are the zeros, build the simplest polynomial you can from those zeros. You know, work backwards. We know that any complex zeros that have imaginary parts, that have i's in them, have to come always in complex conjugate pairs, right? So that's a plus bi and a minus bi. Always has to be that way. Can't be different. Okay, what about this then, right here? Last thing I want to mention. So say we've got this polynomial, this cubic polynomial here, and we want to find the zeros. Well, if we factored that, and you guys could factor that, if we factored that, you could factor it by grouping. You would get x plus 4 times x minus 5 squared. Does that work by grouping? Actually, that one doesn't. That one doesn't. But if I gave you one of the zeros, you could find the others. Okay, we'll just say that. So that's how you would factor this thing. So how many zeros are there? Okay, it almost looks like 2. And if we had talked about this last chapter, we would have said 2. And that's an okay answer. There are 2 different zeros. But what is that telling you? That's telling you that's a multiple zero. In fact, what we say is that the word that we use, and I don't know if this book, I don't think this book uses it, but it's an important word for you guys to know about, is multiplicity. The multiplicity of a zero just tells you essentially how many of them are there. In other words, what's the power of the factor associated with that zero. So if this is an x minus 5 squared, we'd say it has a multiplicity of 2 because it counts as 2 zeros. It shows up twice. And so if we think about it that way, there are our 3 zeros because we knew we had to have 3, didn't we? It's a 3rd degree polynomial. We have to account for 3 zeros. 1, 2, 3. 1, 2, 3. Right? Yes, sir.
So would you enter all 3 zeros in there, or do you really have to enter the second one?
Okay, so it depends. It depends. So now, if I wanted to, if the question says, write all different zeros, then that's what they've always said in the past. Then you would just say -4, 5. Okay, that's fine. If it wants to know, if it said specifically, write all the zeros including duplicates or including zeros with multiplicities greater than 1, then you'd have to write them all. But I don't even know if I'll even do that. I mean, I don't think it's really that important. If you factored it, you would be accounting for all 3 because you'd write it this way, wouldn't you? Right? So you'd have 1, 2, 3 accounted for. Okay? All right. Questions so far? So, fundamental theorem of algebra, whatever the degree of the polynomial is, that is guaranteed to be exactly how many zeros you have. Okay, some of them might be duplicates though, and some of them might be imaginary. Okay? So, let's find all the zeros of, well, we can do this really quickly. Just a little review, that's all this is. How would we find all the zeros of this one? What are your approaches here? There's different ways you could approach this problem. And this, we're getting to a point in math now where we get to start talking about, strategy. Really, there's a lot of strategies for how you could approach this. I'm not saying one's right or one's wrong either. I think I know which way I would definitely do this, but what's a way to do this problem? Find all the zeros. Everything that we've talked about, including stuff we talked about 5 minutes ago, is fair game. What could you do? You could group them, sure. You can see these are going to group, can't you? Right? We could factor this by grouping. That's what I would do, for what it's worth. Not that that's necessarily the best way, just because I would do it that way, but that's what I would do. I would group these things like this, right? And you can see that they are going to group. If I group these and factor by grouping, what's my greatest common factor going to be from the first group? X squared. My leftover? X plus 3, good. And then over here, my leftover, if it exists, if this works, has to be X plus 3. What would go out front? Yeah, 16. Everybody agree? Right? Everybody good with that? So then what does this factor into? Maybe that's better color. So I'm going to get X plus 3 times what? And don't lose sight of the fact that the whole time, really, we're just working on the left side of an equation, right? So this is all equal to 0. So if I solve this, then what are my zeros going to be?
-3 and you're gonna get.
Okay, I'm going to get 9, but that's okay. Say we want to get the zeros, even if they're imaginary. I'm not specifying just real zeros, all zeros.
Plus or minus 4i.
So x equals plus or minus what? 4i, good. So there are my 3 zeros, right? Okay, makes sense? That's a great way to do it because we recognized right away that we could factor by grouping. Factor by grouping is pretty easy. Now, what if we couldn't factor by grouping? What would our only other option be? It's not a great option, but what if that didn't factor by grouping? What could we do? How could we get, all we need to do is find 1. If we could find 1 0 and divide that out synthetically, I'd be left with a quadratic that's easy. What would it be? Okay, the P over Q formula, the rational root theorem. I'd have to find, now that would be horrible this time though, wouldn't it? Potentially. 3 we would have found pretty quickly, so it would have worked, but look at all the possibilities. All the factors, positive and negative factors of 48 over 1. Oh, man. 48, 24, 16, plus or minus, 48, plus or minus 24, plus or minus 16, plus or minus 12, plus or minus 8, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, plus or minus, that's a lot. There's a lot to try there, right? So that would be a mess. But that would be our only other legitimate strategy, okay?
Is there a function in a calculator to do synthetic division?
Not to do synthetic division, but remember that we also have, remember that poly smoke program I showed you, right? Do you remember that one? Okay, I'm gonna, if we have time today, I'll show you that again. I don't know if everybody got a chance to see that or not, but it's pretty slick. Okay, so we'll do away with that. Okay, so now, here's the only other new twist on it, and this is easier though. honestly, you guys you're on the downward slide in chapter 6. You have done, in terms of the effort in chapter 6, I'd estimate you've done 90 to 95% of the chapter is done. From here on out, it's much easier. The hardest things you do, by far, in my opinion, is the stuff that you're either just finished or are finishing now. This is really not very hard. To turn this around backwards, factoring is always harder than expanding, right? They're opposite processes. Multiplying things out, wouldn't you agree multiplying polynomials is a lot easier than having to factor polynomials? Well, that's all, this really is going to just amount to a multiplying polynomial problem. If I want to write, now listen, these directions are a little cryptic, so let's sift through this. We want to write a polynomial function of least degree, okay? So we want to make it as simple as possible, that has real coefficients and a leading coefficient of 1. AKA, boy, that all boils down to the simplest possible polynomial. Well, the simplest polynomial that has zeros, -1, -2, and 2 would be what degree? 3. How come? And how come? 3 zeros, right? Now, we could make a harder one that has other zeros too, but we're not wanting to do that. We want to make the easiest one. So then the next part of this is just, if these are my 3 zeros, we just have to start with the simplest factors we could build from those zeros. So what's going to be the simplest factor we could build from the 0, x equals -1? X plus 1, right? That makes sense? It's always just going to be x minus the 0. So x.
It was just slow, so you started
Yeah,
out and then you're
right, it does that sometimes. So x plus 1, and the reason for that is, think of it this way. To find the 0, don't we always set the factors equal to 0 and solve? So that's the one we'd set equal to 0 to get -1 for an answer, right? Okay, so we get, there's one of our factors. What's the factor from -2? X plus 2. And what's the factor from +2? Okay, now if we want to build the simplest polynomial with those factors, aren't we just undoing the hard stuff we've already done? Right? What we would have done in the past is started with some cubic polynomial and worked really hard to break it apart into factors. But we're assuming that that's already been done and now we just want to go backwards. What would we do with this? Multiply them together, right? So all I have to do is just expand those out, right? Because expanding is our polynomial word for multiplying. Expanding means we're going to multiply stuff together and make a polynomial, right? Factoring means start with a polynomial, break it apart into a product of factors. Now, be smart about this. When you're multiplying out factors, you can a lot of times make the work easier. There's definitely a preferred order to multiply these. Which 2 should I multiply first? No. Last 2. How come?
Because the letters of your numbers.
No.
Negative.
What's the word? So what's that word? What are they?
There's
No. Come on now. This, you honor students, come on now. What's the word? A plus B, or x plus A and x minus A, or A plus B and A minus B. What are those called? Conjugates. They're conjugates. These are, now they're not complex conjugates, so they don't have i's in them, but they're just conjugates, right? If I multiply conjugates out, that's one of our patterns. What's A plus B times A minus B always equal? This is what we call the conjugate pattern. Now it's going to start to all come together for you a little bit, if it already hasn't. What's that always equal if I FOIL it out?
3 squared plus 2 squared.
A squared minus B squared, right? The cross terms, the O and the I and the FOIL always disappear when you're multiplying conjugates, right? So that makes, you see my point, those are really easy to multiply. So what do we get when I multiply these out? Yeah, so x squared minus 4, right? So first of all, it's easier to multiply those because they're conjugates. Next of all, when I do multiply them, I only get 2 terms. So now it's easy to expand these out, right? So then I just get, if I multiply those out, I think I actually, maybe I even did this one. I think I did. I think I built this one. I did. How about that? So there's our x squared minus 4. If I FOIL it out, I just get that, and I'm done. Okay, easy, right? No big deal? Okay, what about this one?
Okay.
Okay, this looks a little trickier because I've got an I in it, but I's, we know how to deal with I's. I's are just numbers. We know how to do the arithmetic of I's. So this time I have zeros of 1 and 3i. Ah, what?
They always have the.
Ah, and you thought correctly. Complex numbers with imaginary parts always have to come in complex conjugate pairs. So what if I wrote this out in its a plus bi form, in its longer form, what is the complex number 3i? No, I don't want anything fancy like that. Like, for example, 1 is really just 1 plus 0i, right?
Right, and so 3i is just 0 plus 3i.
Just 0 plus 3i, isn't it? Right? The real part is 0, it doesn't show up. The imaginary part is 3i. So if 0 plus 3i is a 0 of this thing, then so must be the conjugate 0 minus 3i. Right? Does that make sense? And so we could just more simply write that as a negative 3i. With 3i, we also have to have a negative 3i. They must come in a complex conjugate pair. Ah, because I was being tricky. Okay, because it's implied. You had to see it, and you did. Because we know that if there's one imaginary 0, then we also have to include, even if it's not included originally, we must include it. It's implied. It has to be there. Right? So we have to add this other 0. But now, we don't need any more, do we? That's all that are required. We could add more, but we want to make the simplest possible function. So we'll just keep those 3. But we had to have at least those 3. We couldn't just have 2 because one of them is imaginary, right? Now we just do the same stuff we did before. Just create the factors from those. So x minus 1, x minus 3i, x minus negative 3i, so x plus 3i. Which 2 would I certainly multiply first here?
The last 2.
The last 2. And so it's always going to be that way with imaginary zeros because they always come in complex conjugate pairs. They're always going to form conjugate factors. So you always multiply those first. So if I FOIL those out, what am I going to get? Minus 9i squared, which is the same thing as plus 9 because I squared is negative 1. Good. Okay, so that just becomes x squared plus 9. Expand that, multiply that times x minus 1, and we'd all get that. That third degree polynomial.
After you get to that point, do you have to have the parentheses?
No, you wouldn't. You're right. You wouldn't. They shouldn't be there. Good point. Okay?
What if the leading coefficient isn't 1?
Well, you'll always make it 1. Yeah, you have the freedom to do that. Unless we had a fraction in here, but I won't give any fractions. Okay, so what about this one? Okay, now this time I gave them all to you, right? Here are I have these complex conjugate factors, or zeros. Creating the factors, though, is going to look a little strange. We're going to follow the same pattern as we did before. The first one is just going to be x minus 1. The second one is going to be x minus the quantity negative 2 plus I, right? And the third one would be x minus that whole thing, minus that 0. X minus the quantity negative 2 minus I. So what do we do with that? Okay, here's what you can do that makes this a lot easier. Now, this is a great trick. Pay close attention because this is not obvious, but it's not hard either. So what we do with this, I'm going to do this by hand so I can write it a little bigger. I'm going to put these in, I'm going to enclose them in brackets so the parentheses don't get confusing. So x minus the quantity negative 2 plus I times x minus the quantity negative 2 minus I. So all you do is distribute the negative sign in here. So this factor becomes x plus 2 minus I. And this one becomes x plus 2 plus I, right? Now watch this trick. If I regroup those 3 terms, I can make those look like complex conjugates. What if I group them like this? See that trick? It looks like a minus I times A plus I this time, right? You see that? So now when I multiply these out, they're just conjugates. They fit the form A minus BI times A plus BI. And how would those expand? It'd be minus B squared I squared, so just plus B squared, right? Remember a little bit ago when I said, I told you something here, and I want to just make sure this is very clear. We said that whenever we expand out conjugates, just regular conjugates, we always get A squared minus B squared, right? Now let's extend that and let's look at the specific case of complex conjugates. If I have A plus BI times A minus BI, then that's going to give me specifically A squared minus B squared I squared, but I squared is always negative 1, right? And so every time you multiply complex conjugates together, you always get the answer A squared plus B squared, okay? It just changes that sign, doesn't it? But otherwise it's the same pattern. Okay, so if we go back in here then, we know that this is guaranteed to be, if I expand those out, I'm going to get A squared plus B squared. What's B? B is the coefficient of I, so what's B? 1. What's A?
X plus 2.
The quantity x plus 2. Look how easy that is, right? Otherwise, that's pretty hard. Otherwise, if I didn't do that trick, if I didn't regroup these, do you see how much harder that is? If I didn't regroup, and I want to multiply these out, I'm effectively having to multiply out trinomials, right? If I have to multiply this trinomial times this trinomial, I'm going to get a lot of terms that I'm going to have to wade through, finding like terms, right? You see what I'm getting at? It's a lot easier if we can treat these as a conjugate. So we just regroup. And now when I expand them out, I'm multiplying conjugates, and so I just get A squared plus B squared. Right? Easy. X plus 2 squared, what's our pattern for a binomial? A plus B squared is what?
2x.
Ah, come on, people. This is, you gotta know these things. You can see we need another memorization quiz on this here. So, A plus B squared equals what? No. 2AB, right? Plus B squared, okay? So then this is gonna work out to just be x squared plus 2 times x is 4x, agreed? Okay. Plus b squared, well that's 4, plus 1 is 5, right? So that ends up being pretty easy. And then of course we also have this x minus 1 factor that's out front the whole time. And so we just multiply that through and we got it. Okay, make sense? No, we never did that. Remember, all we did, we just focused on this part right there. We always start with that. Okay?
Where'd you get that? 4x. Okay, never mind.
Okay? And so, do I have those steps in there? I think I do. Yeah. So this is a pretty good PowerPoint. I'll put this one up there. This is a pretty good one. This whole.
The stars is very active. Background is active.
Yeah. That works okay though. That's a. Yeah, this is a good one. This is one you could look back at and it's very accurate. It's good. So, okay, let's try one of these. I think that's it. Oh no, it's not. Okay, try this. Okay, talk me through this one. Let's do this one. We can do this, then I think we're good. If we can do this, we're good. We'll just go to the lab tomorrow and let you work on this stuff. Okay, so what are my, talk me through this then. What are my zeros, or my factors gonna be? What are my zeros, first of all? Is that a complete list?
No, we also have 2 minus.
Oh, okay, good. I've got 4, 4, 2 plus I, 2 minus I. Why does the 4 have to be in there twice?
Because it's a 4 squared.
It's got, yeah, because it's associated, it's got a multiplicity of 2, so it's associated with a squared factor then, isn't it, right? So these two combined, how could I write those? What are the factors that go with those? X minus 4 times x minus 4, right? So I can put a square there, okay? These guys here, now, what am I gonna do with those? X minus,
Same thing we did last time.
same thing we did last time, yeah. Make these brackets. X minus the quantity 2 plus I times x minus the quantity 2 minus I, right? Now what's my trick? Distribute the negative and regroup as complex conjugates, right? So if I distribute the negative, I just get what? Minus 2 minus I. Here I get minus 2 plus I, right? How do I regroup? Okay, so there's my A. There's my A. There's my B, right? Okay. Make sense? So now really all we have to do is just expand that stuff out, right? Okay, so you walk me through this. So what's going to be, let's just focus on this part. That fits, those are conjugates. So they're going to expand to what?
A squared plus B squared.
Okay, a squared plus b squared, and what's a? X minus 2. Okay, plus, right, because we got complex conjugates. Plus 1 squared.
Which is 1.
Everybody, now, questions on that? Does that make sense? Okay, and all this is coming from is that, right? If we multiply complex conjugates together, we always get a squared plus b squared for our result.
Which is our A
Right.
squared plus 2A plus B
So
squared.
there's our a plus negative 1I, right? Or a minus 1I, a plus 1I. So a, there's a, there's b, right?
Okay, so now we
The result is just a squared plus b squared. And then out front I have to include, you know, we're not gonna do anything with it yet, but I've got my x minus 4 squared. So let's focus on this.
Alright, so we have A squared plus 2A plus.
So if we look at x minus 2 squared, there's more a's and b's, right? More complicated. That's just a plus b squared. A is x, b is negative 2. So x squared minus 4x, everybody see that? Plus 2 times x times negative 2. 2 times x times negative 2 is negative 4x, right? Make sense? That's just that expansion, binomial expansion. Plus negative 2 squared plus 1 squared, right? Which is just
Same thing we got last time.
x squared, it is, how about that? X squared minus 4x plus 5,
Same numbers.
x minus 4 squared. And so this is gonna end up being a big polynomial product in the end, isn't it? Here I've got to expand that out. What's x minus 4 squared? X squared minus how many? 8x, right? 2,
Right.
a squared minus 2ab, so 2 times x times negative 4 would be negative 8x plus 16, b squared. Okay. Times okay, now that's just, I'm not going to do that, but I mean, we know how to multiply those out. We've got a lot of practice. Okay?
Calculator thing?
Calculator thing. Yeah. Probably
Yeah,
not.
we have 2 minutes.
Probably not. Probably don't have enough time.
Oh, it'd take that long to get a TI thing.
Yeah, no,
I agree. to right there, that one.
Yeah,
Well,
we
we packed a
didn't
lot of
wanna
math in
give
one
you
period,
that.
didn't we?
Oh, that was really
A lot of stuff.
Oh, it's new.
We got orange now.
Yeah. Is that the color you want for the day, or you want something different to go with purple there? What do you think?
No, it's just. It
In
goes
case
with
the
the
color.
original color you were working with, and then you're ready.
There you go. Okay, so we want to find the zeros of that function. Go to apps. Go down to polysmoke 2. If you don't have it, I'll get it for you. So, so there it is. This is really great. Now, obviously, this is only on the graphing calculator portion of the test. You can press any key. So we want the number 1, the polynomial root finder. It does a bunch of stuff, but we really just only use that first one. So what's the order of our polynomial? Order means same as degree.
3.
3. Okay.
Yep.
Oh, okay. Now look at this. You can even choose imaginary solutions. So you can have it give you back the reals and the imaginaries in A plus BI format. Then you just go down and, well, we'll finish it up tomorrow. It's from there you could do it.